Sir, good morning, sir. Good evening, sir. Vikram, sir.
Yeah, good evening, sir.
Sir. Actually, it is under mute. That's why I couldn't observe.
Oh, okay.
Thank you for joining, sir. Thank you very much, sir.
Okay. Thank
Sir,
you. Shall I start now?
Sir, before that, I request Naveen to introduce our today's resource person, Narsim Denkaran, sir. Please, Naveen. Sir, he will introduce later. You please,
Okay.
sir. Yes.
It's a great pleasure to introduce speaker of our today's program, Dr. Shanmugam Dinakaran. Dr. Shanmugam Dinakaran is a professor in the Department of Mechanical Engineering at IIT Indore. He completed his graduation from the University of Madras, PhD from the IIT Kharagpur. He has worked as a postdoctoral researcher at the University of Valenciennes in France, the University of Porto in Portugal, the University of Minho in Portugal, and the University of Pau in France before joining IIT Indore. He has 5.5 years of postdoctoral experience in total. His areas of research include computational fluid dynamics, heat transfer, bluff body aerodynamics, heat transfer in porous media and microfluids. He has guided 4 PhD students in the area of CFD. He is the coordinator of IIT Indore's Center for Fluid Dynamics. He serves as a reviewer for several journals, including Energy Conservation and Management, International Journal of Heat and Mass Transfer, and other reputed international peer-reviewed journals. He has conducted several short-term courses in CFD. He has also coordinated numerous GAIN courses in the area of thermal science and engineering. He has received external grants from DST, SERB, and CSIR, and other agencies. Now I request Dr. Shanmugam Dinakaran sir to take over the session. Thank you.
So thank you for giving an introduction about me. I thank Professor Ravi Kiran for giving me an opportunity to present some of our works that we do. I hope my slide is visible to everyone.
Yes, sir, it's visible.
Okay. Thank you. I'll be giving about 1 hour lecture on flow around bluff bodies. So this is mainly an computational work. We work in the area of computational fluid dynamics. We do simulations using finite volume methods, lattice Boltzmann methods. So we use both the ANSYS Fluent and OpenFOAM software. So what you are seeing here is a streamlined body. So let me turn off the video. So you see, on the right hand side you see a fish, okay, and a bird on the left hand side. So these are all streamlined bodies. Okay, you can see the shape. So the fish can swim easily in water, and also the birds can fly. This is another example of a streamlined body. You see a cockroach here. Although it cannot fly for a longer distance, it has a streamlined body. Similarly, this moth. Okay. So this figure is about a tree. Okay. So that has oriented itself according to the wind flow. So you can see that nearby this tree, there are no other trees. So accordingly, due to this wind flow, it has bent something like this. So these are some of the streamlined, man-made streamlined bodies. And this one is, it's a high-speed train. Okay. This one is the Concorde flight. You see a bullet here. Okay. And this is a bus whose shape has been optimized to reduce the drag. Okay. Similarly, you see a race car over here. Okay. And also you see, usually when children or when we ride a bicycle, what we usually do is we try to bend so that there is less resistance to airflow. These are called as blunt bodies. Okay. As we know, these birds cannot fly, either because they do not have wings, and the main reason is that because of the shape of the bodies. You can see the shape. It's not an aerodynamic design here. You can see the shape here. Okay. Even an ostrich cannot fly. Okay. So you can see the difference between this bird, or this one, and this one. These are all called blunt bodies. Another example of man-made bodies that are, these are some of the structures. You can see this building. Okay, this is a blunt body, and a truck, bus, and even this transmission pipelines are called as blunt bodies or plug bodies. Okay. This is a mimetic structure that is found in Hyderabad. That this building belongs to the National Fisheries Development Board. This blunt bodies, as I told you, there is a significant difference between the streamlined body that you can see here, the fish, similarly this tree, okay, these vehicles, and the birds here. The bluff body flows. What is a bluff body flow? Whenever a fluid flows past any blunt object, so that is called as bluff body flow. So here you might be, you could see that this is a shell and tube heat exchanger. Okay. So you have the shell, that is the outer covering, and you have the tubes. So these tubes carry hot water, for example. Okay. And over the shell, when cold water is passed through this shell, what happens is that when cold water flows inside, it flows over these tubes, and then it gets warmed up and it is removed from here. So this is an example of flow over a blunt body or a bluff body. Similarly, you have the car radiator, in which we have several tubes inside. Both external flow also occurs, and heat transfer internally also it takes place. So when air flows over a vehicle, okay, in which you have a car radiator and you have the fins over here, so this is also an example of flow over bluff bodies. Okay. Similarly, we have the electronic components. Say if you take the CPU, inside the CPU we have the electronic components. And when the fan is turned on, or automatically when the temperature inside rises inside the CPU cabinet, the fan turns on and air flows over this body. Okay. This electronic component can be taken as a blunt body. So these blunt bodies or the bluff bodies have practical applications. So it is important that one studies the flow as well as heat transfer characteristics. So that is the reason why so many people you find thousands of or even lakhs of papers are there in the area of bluff body flows. You could see two objects over here. On the left hand side is the bullet. On the right hand side you have a brick. Okay. So when air flows over a streamlined body such as a bullet, so flow would be smooth. There won't be any much disturbance in the flow. But when a fluid flows over a bluff body, such as this one, a brick, what happens is that the complex fluid flow phenomena takes place around this body. There will be a huge differences here, and there would be a recirculation region behind this body. You can see here, different birds are shown when they fly. Okay. You can see the drag coefficient. So when it is more streamlined, as you can see here, the drag coefficient is something like 0.05. When it is more bluff, the drag coefficient increases. Okay. So this means streamlined bodies have less drag coefficient or resistance to flow, unlike the blunt bodies that have very high drag coefficient. They offer more resistance to airflow. Here you can see two different designs of a vehicle. This is more streamlined, and this flow around this vehicle is more bluff. Okay. So you can see here, a separated region is seen here, and the flow is also, in case if the velocities are very high, the flow will be turbulent over here. So in this case, the object itself is more streamlined. You don't see any large separated region. That means the drag would be lesser over here compared to this car. In the coming slides, I'll be explaining you what happens when fluid flows over a bluff body. As I told, flow over bluff bodies finds practical applications in cooling of electronic components, in heat exchanger designs. You see here, what you are seeing here on the left-hand side is the flow characteristics for the flow faster cylinder, a two-dimensional cylinder. You assume a curtain rod, for example. You take a curtain rod, long curtain rod, and you put a fan in front of it. When fluid flows over this curtain rod, in two dimensions, this would look like a cylinder. So when the Reynolds number is very low, what happens is that fluid flows over the surface, it climbs over the surface, and it traverses down. In case if you're going to increase the flow velocities, what happens is that a boundary layer is formed over the surface, on the surface of this blunt body, that is a cylinder, and this flow separation, flow separation occurs over here. As a result, you see two recirculating eddies behind this cylinder. This is something like during the summer season, when you try to cross the river, when the water level is less than the knee. So you could see that behind your leg, you could see two recirculation regions. The water will be rotating. So that is called as the separated region. Okay, the flow velocities will be negative because fluid moves in the negative direction. It keeps rotating. When the flow velocities are further increased, what happens is that the vortex that is formed on both the surface, on both the top and bottom surface, it gets separated and then it starts shedding. I'll show you a slide in the next coming slides. I'll show you this phenomenon. With further increase in Reynolds number or the flow velocities, what happens is that flow becomes turbulent. In case of laminar flow, say for example, up to this one, say if you take the Reynolds number range, something like up to 3000. So flow is laminar and unsteady. And in case if this body is hot, what happens is that heat gets removed. Because when you take any hot object, when you blow air over it, automatically it gets cooled. Okay. In the same way, heat transfer occurs. In case of turbulent flow, when the flow velocities are very high, you find a large number of eddies formed behind this cylindrical body. Intense mixing takes place. As a result, more heat transfer enhancement would be there. So this one, on the right-hand side, you see the flow around a circular cylinder for Reynolds number 10, 20, and 40. You see that, you observe that the recirculation region, as I told you, whenever you try to cross a river during the summer season, when the water level is not very high, when the flow velocities are steady, when the flow is steady, you find some recirculation regions behind your leg. Okay, the same thing happens here. So this recirculation region, with increase in flow velocities, it keeps on increasing. You can see the recirculation region here, whose length is increased at Reynolds number 40 compared to Reynolds number 20 and 10. Okay. So same thing I've shown here. You can see here for the flow past a cylinder, you find a large wake region. So, I mean, separated region is the region where flow recirculation occurs, and the wake region is the region where you could see the flow disturbances. That is, the effect of the body would be felt in the on the velocities. Okay, again, similar image. You can see this is a circular cylinder. That is a blunt body, and here you could see a streamlined body. So this picture shows that the skin friction coefficient in case this bar, okay, this one shows the amount of skin friction coefficient, that is the effects due to friction that is taking place on the surface. Okay. You see a large rectangle over here. So this is the pressure drag as shown here. A blunt body has a smaller skin friction drag, but a larger pressure drag, because what really happens is that when a fluid flows over a blunt body, a very high pressure, okay, is, I mean, a large forces are exerted. I mean, the pressure forces are very high on the front surface. On the rear surface, what happens is that since this body is blocking the flow and the fluid is recirculating, the pressure is low over here. Okay. So this pressure difference gives rise to the drag forces due to pressure. Here you can see the stream. This is a streamlined body. You can see here. For a streamlined body, since the surface is large, okay, and at the same time, the skin friction drag, the viscous drag is more compared to the pressure forces. As a result, you can see that the bar over here, okay, for the skin friction drag is higher compared to the white rectangle over here that corresponds to pressure drag. That means in case of a blunt body, the drag due to pressure would be very high compared to a streamlined body. Similar images. You can see a car over here. Okay. So this is the side mirror. Okay. The side mirror also contributes to drag. Okay. I read in, I mean, somewhere I read that this side mirrors, okay, side mirrors also contributes to more drag force acting on this one. It seems, you know, it accounts for 7% of the drag on this car. So in foreign countries, some this car companies, so what they've done is they have, they have removed this side mirrors. So instead, they have placed cameras so that, you know, I mean, the drag can be reduced. The drag due to the side mirrors reduces, and so we can save some fuel. As I told you, the in case of blunt bodies, the drag due to pressure forces is very high. These are some of the structures, I can say, or vehicles or entities. So whose drag coefficient is given? We see here from the extreme right hand side, this is a streamlined body. The streamlined body has a drag coefficient of 0.05. You can see this is more bluff in nature. As a result, the drag coefficient is 0.35. This is more or less like a sphere. This one is a sphere. This is a vehicle. And this one is a truck, a scooter, and a human being. This is a square, say a cube. This can be a disc. If you see here, this is something like a large pillar. So when fluid flows over the surface, a large pressure forces would be exerted on this space. As a result, the drag coefficient is much larger for this one. So this is, the water shedding. Okay. So what really happens is that, to go back, when fluid flows over a blunt body, such as a circular cylinder, flow separation takes place, and this vortex, it keeps on growing. When it reaches certain Reynolds number, it cannot be symmetric for longer. Okay. So the vortex that is formed on the surface, it becomes unstable and it starts shedding. Okay. So here this one is a streamline, this is not a vortex. So you have a circular cylinder here and fluid flows over the cylinder. Vortices are formed on the top layer as well as the bottom layer. So this green colored one is the top vortex and the pink colored one is the bottom vortex. In case of steady flow, this vortices always remain attached to the surface. In case of unsteady flow, what happens is that the strength of the vortex, so vortex is nothing but the recirculation. Again, I gave an example. If you cross the river during the summer season, so behind your leg, you can see the vortices. The same thing is shown here. So the vortices, what happens is that when the fluid velocities are very high, the vortex on the top surface, it grows, and then the bottom surface also, the vortex grows. The top surface vortex, it becomes, after some time, it keeps on growing and becomes unstable. Okay? That is the reason why you can see it is cut off from the main cylinder and it is shed, you can see. So you see a row of vortices. Okay? The green colored vortex on the top and the pink color vortex on the bottom. Okay? So whenever the vortices are shed, as you can see, whenever the vortices are shed, what happens is that in case if the object is hot, the heat would be transferred. Okay? The vortex, it carries the heat at its center. Okay? And then when it is shed, that means the heat is also removed. Okay? This phenomena is called as von Karman vortex street or the vortex shedding phenomena. Okay? And this alternating row of vortices is called as von Karman vortex street. Okay? So this vortex shedding phenomena finds application in cooling of electronic components, because if this object is hot, when fluid flows over the surface, these vortices are shed. As a result, these vortices will carry away the heat from the body. This is one of the videos in which a bridge sways due to aerodynamic forces acting on its surface. You could see this bridge is swaying here. It is mainly due to the forces acting. One is the viscous forces or the shear forces. This is a video of a destination USA due to the aerodynamic forces. I'm playing this video.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
This bridge collapsed in USA due to the unsteady aerodynamic forces. As I told before, flow around Bluff bodies finds applications in cooling of electronic components. Some of the electronic components are shown here. Okay, condensers, resistors. Okay. You could see this is a CPU cabinet. This is a fan. Okay. So when the temperature of the electronic components inside increases, automatically the sensor turns on the fan. Okay. As a result, what happens is that air flows inside. It flows over these electronic components and then it cools them. So how much heat is transferred from this electronic components is measured by the Nusselt number in heat transfer. Again, this one, you have a brick. Okay. When I'm going to turn on a fan, air flows over the surface and the forces are going to act on this one, on the surface. I'll draw and show you the different forces acting on the surface. When air flows, so this is the pressure force acting on the front surface of the Bluff body. This one is also the pressure force, but it acts the opposite direction. This one is the viscous force acting on the top surface or the shear force. Similarly, this one is the shear force acting on the bottom surface. Again, I repeat, pressure force acts on the top surface. Pressure force act on the rear surface. The viscous force act on the top surface and the viscous force act on the bottom surface. Okay. So all these forces you can see, they are in the horizontal direction. So this gives rise to drag. So drag is due to the pressure forces on the front and rear and the viscous forces on the top and bottom. Similarly, what happens is when a fluid flows over the surface, shear forces also act on the surface. I'll draw this. This is the shear force acting tangential to the surface. I'll mark it in red. So this force will try to push the body up. Similarly, the viscous forces act on the rear surface also, but in the opposite direction. The same way, pressure forces act on the top side and also on the bottom surface. So this one is the shear force. Sorry, shear force, pressure force, and the shear force. So if you see the arrow marks is either up or down. So these forces contribute to lift on the body. So once we are able to know the pressure forces acting on the body as well as the velocities, so from the velocities we can find out the what you call the shear stress. Tau is equal to mu dou A over dou Y. Firstly, I'll be showing you one of the works that we have done. Okay. It's on Bluff body flows. It's a very simple geometry. So what you see here is a square body that is placed close to a moving wall. Okay. This is the same as you have a car. For example, this. That's fine. Okay. You have a car. Okay, this car is considered to be a bluff body. I take it as a square body. Okay. And there is a gap in between. And at the bottom also, at the bottom you have the road. Okay. So I can do a simulation. Instead of taking the actual geometry of the car, I can take a square body or a rectangular body. Okay. So in this case, when the car moves, the road is stationary and the car is moving. Okay. The similar configuration we have taken here. You have a square body. Below it, you have a plain wall. That is, you can take it as a road. So this wall is moving. This wall is moving and this cylinder is stationary. Okay. It's the same as the wall is stationary and the cylinder is moving. That is, the car is moving. Okay. So what we did is we varied the distance between the cylinder and the moving wall. Okay. So we did a CFD simulation. We used our own code. Okay. So we assume that the flow at the inlet, the fluid is flowing at a uniform flow at the inlet. Okay. And this one is the mesh. You could see when we do a CFD simulation, what happens is that close to the body, okay, a large gradient in temperature occurs. So one has to take a fine mesh over here. You could see far away from the body, the velocities won't be changing. So what we have done is we have taken a coarse mesh over here. Here you see a very black region because the mesh is very fine. Okay. So what we did is we varied the distance between the cylinder and this moving wall. Okay. We varied it from 0.1. Okay. G is the distance between the cylinder and the wall. So we varied it from 0.1 to 4. I'll show you some of the configurations here. This one. This picture, whatever your image that you are seeing here, is the vorticity contour. And this image is the isotherms, constant temperature lines. You could see the vorticity pattern here. When the cylinder is far away, okay, when the body is far away from the wall, you could see the vortices that are being shed. So this is the top vortex, and this one is the bottom vortex. Okay. You see a row of vortices found behind the cylinder. In case if the cylinder is hot, what would happen is these vortices, it would take away the heat. As a result, the cylinder will get cooled down easily. So now we try to bring this cylinder close to the wall. You can see here when G is 2. Okay. G by D is 2. G by D is 2 means this gap is twice the size of the cylinder. The size, no, one length is taken as D. Okay. You could see the vortices are formed on the walls of on the moving wall. At the same time, you see a row of vortices. When the cylinder is further moved down, okay, what happens is the vortices that are formed at the bottom surface of the cylinder, they start mixing with the vortex formed on the moving wall. Okay. Further bringing it down to G by D 0.5, okay, when the distance is very close. Okay. So the bottom vortices that are shed, you don't see that one. It completely mixes with the vortices that are formed on the walls. You see only a single row of vortices. Okay. Again, when you further move, what really happens is that this one, G by D is equal to 0.1. That means the cylinder is almost, on the wall. You see a steady pattern. The vortices are steady here. So the observation is when the cylinder is far away for the given Reynolds number or the flow velocity, flow is unsteady and periodic with vortex shedding. When the distance is G by D is say 0.3 or lesser than 0.3, the flow becomes unsteady. So you see unsteady flow pattern here and a steady flow pattern here. Okay. So these are the isotherms. Isotherms follow the same pattern of the vortices because these are the constant temperature lines. You can see the, suppose if this body is hot, you can see close to the square, you see red area. That means it's too hot. Okay. This blue means it's cold. You can see the isotherms around the cylinder for different gaps. This one I told you, the forces acting on the body are the pressure forces and the viscous forces. All the forces that are acting in the horizontal direction gives rise to the drag. Similarly, the forces acting on the vertical direction, up or down, gives rise to lift. We have plotted the coefficient of lift and the coefficient of lift due to pressure forces and the coefficient of lift due to viscous forces. So you could see the variation here. CL, this is the red line you can see here. And this is the G by D, gap. Okay. Gap 0 means the cylinder is resting on the moving wall. Okay. So when you go in this direction, the distance between the cylinder and the moving wall, it increases. You could see that when the cylinder is very close to the wall, there is a positive lift. That means if you do not hold the cylinder, see when it is very close, this is a stationary cylinder. Okay. If you do not hold it, this is a fixed one. If it is not fixed, what really happens is that this will fly up, it will move up because there is a large lift forces over here. You can see when the cylinder is, when the distance between the cylinder and the wall is increased, the lift coefficient keeps on decreasing. That means the lift forces acting on the cylinder keeps on decreasing, and finally, when it is much far away, the forces become equal because it becomes zero. The lift forces are zero. The reason is that when air flows over the surface of this brick, the lift forces would be equal and opposite. Similarly, this is a plot of the variation of drag coefficient with the gap between the cylinder and the wall. You could see that this line is the this blue one shows the variation of drag on the cylinder with increase in gap. Again, when the cylinder is very close to the moving wall, you find that a large number of, a huge amount of drag forces are exerted on the surface. That's why. So then when the gap increases, it drops down. And again, it slightly increases due to the change in flow pattern. Because if you see here, this is unsteady flow because vortices are shed, and this one is quasi steady or unsteady, and this is a complete steady flow. Okay. Due to this change in flow pattern, there is a variation, there is a slight increase in the drag coefficient, and further, what happens is that it keeps on decreasing and it reaches a single cylinder value. This one, Strohal number. Strohal number is nothing but the non-dimensional vortex shedding frequency. I'll come back. You see the vortices here. as I shown in the animation here, the vortices are shed one after the other. Okay, more the number of vortices that are shed from the cylinder, more the amount of heat that is transferred from this object. So we need to know what is the frequency during a given time interval, how many vortices are shed. So that is known to the Strouhal number. You can see here when the flow, okay, when the gap is something like this is 0.2, when the gap is 0.2, Strouhal number is small. When the gap keeps on increasing up to say 0.1, the Strouhal number keeps on increasing. That means the frequency of vortex shedding, it keeps on increasing and it reaches the single cylinder value. Okay. So for gap less than 0.2, say for example 0.1, we see that the Strouhal number is 0. Anyway, it's not mentioned here. It's 0 because vortex shedding does not occur when the gap is 0.1. These are some of the streamlines shown for different gaps. This is the isotherms. These are all instantaneous streamlines and isotherms drawn at a particular instant. Okay. I'll come back. This is the plot of the variation of drag and lift with time. On the y-axis, we have CL and CD. On the x-axis, we have the time. So we do a simulation, say for example, time t is equal to 0 seconds to 100 seconds. When we run the simulation, we plot the variation of lift coefficient. Okay. You could see that this is oscillating for gap 4, gap 2, gap 1, 0.5 and 0.4. When the cylinder is very close, you could see that these oscillations are not there. The unsteady forces are not acting on the surface because the flow becomes steady, as you can see here. When the flow becomes steady, the variation of lift, CL, okay, CL is the dotted line and CD is the solid line. Okay. So when the flow becomes steady, this also becomes a straight line. Now, we were interested in knowing the amount of heat transfer from the surface of this body. Okay. This plot shows the variation of heat transfer as a function of time. You could see when the cylinder, when the gap is 0.2, the flow becomes steady. As a result, the Nusselt number also becomes steady. So this one is the variation of the Nusselt number. Nusselt number is nothing but the ratio of heat transfer in convection to the heat transfer in conduction. We're just comparing. Okay. So in conduction, if this is the amount of heat transfer, and in convection, how much times it has increased. So Nusselt number plot, variation of Nusselt number is shown on different phases. So AB is the front face, BC is the bottom face, CD is the rear, and DA is the top face. You can see that when air flows over the body, it impinges on the front surface. As a result, what happens is that the Nusselt number, the local Nusselt number values are very high because a cold fluid impinging on a hot surface, straight away it comes in contact over here only. So as a result, more heat is removed from here. Okay. Then on the top corner A over here, you have the highest heat transfer for 0.1 because the cylinder is very close and fluid climbs over the surface. We have the lowest heat transfer on the rear surface because of the recirculating fluid. This one shows the variation of mean Nusselt number with gap. You can see here. So this mean Nusselt number is very high. It's something like 5.4. That means compared to conduction, the heat transfer in forced convection or convection is 5.5 times nearly. Okay, that is the highest when the body is kept at a distance of 0.1. Okay, then it keeps on decreasing. It slightly increases due to change in flow pattern, and then it achieves the single cylinder value. That means when I'm going to keep this body very close to the wall, I would achieve very high heat transfer rates. Say, for example, in case if you take the electronic components in the CPU cabinet, what you can do is you can keep, suppose you have a motherboard over here and some electronic components fixed over there. So when you keep it very close to the wall, say for example over here, when air flows over this electronic components, the heat transfer would be highest when the gap between the body and the wall is very high. You can see here. When the gap is 0.1, the enhancement is something like 28. And then it slightly decreases. Then due to change in flow pattern, it increases. And finally, it reaches a single cylinder value. This is all about flow around a single cylinder near a moving wall. Okay. So this is relevant to flow around vehicles as well as cooling of electronic components. I'll stop now.
Sir, is it over, sir? Or continuation, sir?
Lecture is over, sir.
Thank you very much, sir. Even a small layman can understand by your valuable session. It's really useful, sir.
Okay.
From fundamentals to start. I request all the participants. Feedback form will be given later. I request any questions are there, you please ask, sir. Sumande, any question? Daughter Rakesh Kumar?
No, sir.
No, sir.
Every day you are asking question. I think you don't have any question today. Sir,
It's
I
not
think
like
you have clarified very nicely, sir.
Okay.
Okay, sir. I will ask a question related to optimization. Can we optimize these curves, or what you're talking about, like the drag versus?
Yeah, it can be done. It can be done by using an optimization algorithm, shape optimization algorithm.
Like, is there any state of the art in this domain, like using optimization technique, be it non-gradient optimization techniques, to optimize these curves so that we will come to know what are the parameters which give those optimized function for the problem concern?
Okay. So I have not worked on optimization, but I know people work on optimization, shape optimization. So there are some algorithms. So what it does is it changes the shape of the object. So you have to tell what is your desired thing. Like if your desired thing is objective is the drag reduction, so you have to give that parameter, and automatically this software, this algorithm, it would optimize your shape.
Like
I do not know which software it is, but I have seen people working on it.
Like level set functions where it will track the shape what you're talking about, sir.
Maybe, but I do not know the technique.
Okay.
What technique it is?
But it's possible, no, sir?
Yes, it's possible. It's possible.
Okay, sir. Thank you, sir.
Okay. So, Professor.
Actually, Santosh, sir, actually, out of all the days, I cannot say, but sir given very nice presentation. Even layman can also understand sir's presentation. You all of you can share this YouTube link, sir. It is also available in YouTube link, sir.
I saw
Santosh,
it.
you want to ask some question? Santosh.
No, sir. No, sir. I don't have any question, sir. Indeed,
Sir,
it
thank
was
you very much, sir.
like sir
Okay.
has explained clearly, sir.
Okay. Thank you.
Sir, only 2 minutes, sir. I am interrupting.
Okay.
My dear, all the participants from day after tomorrow, offline session is there. You kindly join, and anybody only. I got a request from Rakesh Kumar only for the hostel accommodation. I feel remaining all are maybe coming from through their relatives, etc. Okay, please participate, and 17th will be nearby small industrial visit also there. I request all the participants. Sir, you have concluded our first session is with H.N. Das, sir. He given an introduction to CFD,
Okay.
NSCL scientist.
Okay.
And another one, Venkat Ratnam, sir, is technical officer in NSCL, Naval Science and Technological Laboratories.
Okay.
He given an introduction to condition monitoring. And 3 sessions are taken by IIT Madras Professor Rajiv Sharma, sir.
Okay.
On hydrodynamic design of vehicles, and your session is on Bluff body, sir.
Okay.
Thank you very much for participating, sir. Sir,
Thanks, sir.
I think by next week I will send some forms, sir. I need your signature.
Sure, I'll do it. Sir,
Yeah,
one more
thank
thing.
you very much, sir. Thank you, sir. And
Okay.
probably any workshop next time, you please visit our NIT Andhra Pradesh, sir.
Sure, sir. I'll do it. Just wanted to ask you. So, is this the last session, or tomorrow also?
In online is the last session, sir, and
Okay.
the remaining are the offline. Sir, tell me, sir, anything?
Yeah. No. Actually, I have one more lecture. I think participants might be going for a dinner now. No, I guess.
No, sir. They can stay if you say up to 9. They can stay. Only I thought. Will you continue, sir? Will you continue?
Sir, what I'll do is, I'll finish it within 15 minutes.
Please, sir. Please.
Okay.
They are habituated up to 9 o'clock only.
Oh,
please
okay,
continue,
okay.
sir.
But they must be hungry. But anyway, I'll finish.
No, sir. They will stay, sir. Please, sir. Please.
Okay, sir.
Please take your own time, sir.
Okay.
You told you stopped. I thought it is finished. You please continue, sir. Sorry for interruption.
That's fine.
Thank you, sir.
That's okay. Okay. Sir, can you see my slide?
Yes, sir.
Okay.
Actually, you followed that time 7:50. Please, sir. Please continue.
Okay, but is there any break like
No, sir. It is online only. They are all staying. Please, sir.
Okay.
All of you, please stay online. Thank you, sir.
Okay, sir. Okay. So this one is about. In the last slide I had shown the flow past a solid body. Okay. So we have also worked on flow around porous bodies. Porous bodies, like I gave an example of curtain rod. So that is a solid body. So in case if the curtain rod is made of a material that is porous, for example, chalk piece if you take. So if fluid flows over a chalk piece, so that is called as flow around porous bodies. Okay. Porous media, everyone knows. Chalk piece is a porous media. Sponge and a bunch of hair. Okay. Flow inside, flow over trees also, no? Because trees are porous in nature. In the sense, no, when air flows over it, you have a lot of gap in between the leaves, so that can also be considered as porous medium. So we have done work on flow around porous cylinders. Okay. Exactly the same as the previous one. In that case, they were solid cylinders, and this one is a porous cylinder. So in case of solid cylinders, the governing equations that you solve, in heat transfer and fluid mechanics, you might have studied. The continuity, momentum, and energy equations you solve in case of solid bodies. In case of porous bodies, we use a model called the Darcy model. So I'm going to give a short presentation on flow around porous bodies. So the practical, this one, what you see here is you see a sea. Okay, it's an ocean, the deep ocean. You see a ship over here. Okay. So what happens is that inside the, for example, inside the ocean, okay, you have this what you call, I'm sorry, just a minute. Okay. So inside the deep ocean, what happens is that the temperature of the water is very low. Okay, maybe like 0 degrees Celsius also. Okay. So whenever this plants and the plants, this in the ocean, when they die, okay, or when the animals die, what happens is they float on the top. So when they float on the top, that's what it's written here, floating dead plants and animals. So when they float on the top, okay, some bacteria and all those things will go and colonize over here. They'll be there. Okay. So this forms as a ice. It's called as a snow. They call it as a marine snow. Okay. So I repeat, when this dead animals and the pieces of flesh or dead plants, when they float, due to the lower temperature, they become snow. And this snow, what happens is it starts sinking. Okay. It becomes an aggregate, as it's written here. Aggregates are formed and starts to sink. Okay. So these are all a lump of ice in which you find microorganisms, because it's flesh, dead flesh, dead tissues. Okay. So what happens is that inside, because of the what you call this flesh, so what really happens is that oxygen and nitrogen are formed, are released from the dead plants or dead animals. Okay. As a result, this oxygen and nitrogen, they form a long trail here. I can see here. So this is the fourth one. Okay. So when the snow sinks, you see a long chemical trail. Okay. So this, what really happens is that this when the snow, this is a marine snow, it's called as a marine snow. There are several microorganisms. Okay. It's something like whose size is around 0.5 mm. Okay. They are called copepods. This one, the small organisms. Okay, like a tadpole-like things. So these copepods, what they do is, whenever they come across this long trail of dissolved substances, okay, they will sense that the snow is sinking, marine snow is sinking, and then they will try to follow the trail, and then they will grow and reproduce here. They will grow for a longer time. Here you can see some of the copepods feeding on marine snow, and they grow there. They say for example, for 10 days or 20 days, and they reproduce. They colonize. A large, huge family would be there here. Okay. So this kind of study on how this marine snow sinks and how the concentration or the dissolved substances leak is of interest to marine microbiologists. These people are called the marine microbiologists. Okay. They are very much interested in knowing how these animals they grow and what is the interaction between the animals and the living atmosphere here. Okay. That's what is their objective. So you see here a marine snow. This is an actual marine snow. It forms like a spherical ball. These are some of the microorganisms. Whenever this spherical ball or the marine snow sinks, the concentration of the substances, oxygen, nitrogen, everything, it starts leaking. So these microorganisms called as zooplanktons, they will try to follow the trail and they will try to grow over this one. Okay. So based on this concept, we try to do a numerical simulation. Again, I'm showing you, this is a marine snow. This is formed on the ocean surface. This consists of dead plants and dead animals, small pieces of flesh. Okay. You can see here, marine snow is sinking from the top of the ocean to the bottom. And these microorganisms they will try to follow the leaking substances. How they identify this snow is sinking is through the leaking substances. Okay. So what we did is we tried to consider a porous cylinder, or I can say it's a porous sphere. I'll say it's a porous sphere. Okay. So we did a similar simulation as I shown you before. This is a porous region. Around this, we took a small domain, a circular domain, okay, in which this is called as the clear fluid region. So porous region here and the clear fluid region. So for the clear fluid region, we used the continuity, momentum, and the concentration equation. So when we solve the continuity and the momentum equation, we get the velocities u, v, pressure. When we solve the concentration equation, this one, we get the concentration distribution. Okay. So specifically, since this is a porous region, we have used a model called the Darcy-Brinkmann-Forstemann model. Okay. This equation is the continuity momentum equation, and the mass transfer equation is for porous region, this region. Okay. When you come to the clear fluid region, what happens is that the porosity here, if you see, epsilon is the porosity, u is the velocity in the x direction. Okay. Again, so this one, a Reynolds number you have, Darcy number you have. Okay. So here the Darcy number is one of the important parameter here. Okay. So Darcy number is the ratio of permeability to the square of the diameter. Okay. So in case if you take a sponge, okay, when you pour water through a sponge, what would happen is water will flow down immediately because it is highly porous, and at the same time, the gap, okay, there are several pores. Between the pores, there is a gap, so that fluid flows through one pore. When the gap pore is open, it goes through the other pore. So as a result, when you pour water through sponge, water will quickly come down. Okay. Suppose, although it is highly porous, suppose you take a sponge, porous sponge, if the pores, which are inside the sponge, if they are not connected in the sense, they are simply voids. Okay, there is no gap between, there is no connection, there is no gap between the other pore. Then even when you pour water over it, if the pores are not open, water cannot flow through. Okay, that means even if it is a highly porous sponge, if the pore is not open, what would happen is water cannot flow. Okay, so this Darcy number characterizes this one. Darcy number is the ratio of permeability. So permeability is a measure of how much the pores are open. You can see here, there are several small circular regions. If there is no link, there is no opening between the pores, that means fluid cannot flow. Okay. So Darcy number 10 power minus 2, I can say here. Darcy number 10 power minus 2 means the pores are open. When you pour water through the sponge, it will come down. Everything will flow down. Okay. But even though the pores, the sponge may be highly porous, but when the pores are not open, what would happen is water will not flow. So that case is taken to be equivalent to as Darcy number 10 power minus 6. It means Darcy number 10 power minus 6 means it's a porous medium, but still the pores are not open, fluid cannot flow through. Darcy number 10 power minus 2 means it's highly permeable. Okay. So based on this, we did try to do a simulation on the flow past a porous cylinder for Reynolds number 1 to 40. Okay, you see here, fluid is flowing over a porous circular cylinder, chalk piece, for example. Okay. At Darcy 10 power minus 6, I could see that water is not flowing inside at all. You can see this one also, Reynolds number 20. There is no water flow or air flow inside. Okay. At Darcy 10 power minus 3, when the pores are open, okay, so fluid flows inside. You can see the fluid flowing inside. Okay. When the body, when the porous body is highly permeable, that is Darcy 10 power minus 2. When the permeability is very high, you could see there's almost like a through flow here. So this simulation has been carried out by solving the continuity, momentum, and mass transfer equation. Okay, so we use the porous media models called the Darcy, Brinkman, and Forscherman model. So Darcy model is usually used for simulating flow in porous medium. Okay, so this one same way. This is we have shown the wake region, the recirculating eddy behind this cylinder here. Okay, this one is at Darcy 10 power minus 3. You can see the fluid that is flowing inside. Okay, and then Darcy 10 power minus 2, you see again a through flow. This is one. Okay, Darcy 10 power minus 6, the same thing. Fluid cannot flow inside. When it is highly porous, fluid almost flows through this body. You can see here. The same way as I had shown in the previous slides, we tried to plot the variation of drag coefficient with time and the variation of drag coefficient with Reynolds number here. Okay, these are some of the comparisons of our study with the existing one. Again, the variation of this length, the recirculating region for different Darcy numbers. Okay. So this one I'm showing you, what really happens is when fluid flows over a surface, flow separation takes place. Say for example, for a solid cylinder, flow separates from the cylinder and you have a recirculating eddy here, okay, at an angle of 120 degrees. But in case of porous body, since there is fluid flow through the body, this angle shifts to the rear side. So that variation in the separation angle is shown here for different Darcy numbers and also for the solid cylinder. Okay, this one. In case of a solid body, a solid cylinder, what really happens is flow separation. I'll show you here. You can see this is at, for example, at Darcy 10 power minus 5, you can see fluid climbs over the surface. Okay. You don't see any recirculation eddy here. Okay. So for example, here. Okay. Here you see a recirculating eddy. So we try to see at what Reynolds number this recirculation eddy appears here. Okay, we found that when Darcy number 10 power minus 2, for Darcy number 10 power minus 2, the recirculation eddy appears at Reynolds number something like 10. Okay. But in case of solid body, the recirculating eddy, you can see here, okay, that appears at around Reynolds number 7. Okay. So this one, I'll come back to the previous picture I had shown before. This one, okay. In this snow, porous snow, when it sinks inside the ocean, whatever contents, dissolved oxygen or nitrogen contents are there, that will leak. Okay. So by solving this mass transfer equation numerically using a finite volume method, so we plotted the concentration contours. You can see here at Reynolds number 20 and Darcy 10 power minus 6. That means you have a chalk piece, you take a chalk piece, you dip it in a red ink, and then you take a tank full of water, and then you drop the chalk piece inside. So what happens is when the chalk piece keeps going down, you would find that on the corners, okay, the dye or the ink, no, it would get washed away. Okay. You can see here. This is at Darcy 10 power minus 6. At Darcy 10 power minus 2, that means it's highly porous or highly permeable, I can say. This one is not permeable. Although it is porous, it is not permeable. It does not allow fluid to flow through. This one does it 10 power minus 2. That means it is highly permeable. You can see at different times, t is equal to 0, 5, 10, 15 seconds. So water flows inside, or when the chalk piece comes down, fluid flows inside and it tries to wash away the fluid. It's simple, like you take a sponge, dip it in ink, and then you throw it inside a well. What will happen is, if it is highly permeable, whatever contents are there inside the sponge, it will come down. The same thing, it will come out. So the same thing you can see here. Okay. We also observe that a long tail is formed of when the concentration trail is formed behind the cylinder, and you can also see that since fluid flows inside the body, it's completely washed away. This we can take it as a marine snow, where the contents are leaking when it sinks down. So I've shown a animation here. This is taken as a marine snow. You see here. These copepods, microorganisms, the large ocean is very large. What they do is they like to feed on this marine snow. They will keep on moving here. Okay. When they keep on moving, when they come in contact with this long leaking substances, they immediately know that, oh, this is marine snow is sinking. I have to go, and then so here is where the marine snow is. I can go and feed on it. I can reproduce. So that's what happens in the ocean. This one again, I'm showing you. This marine snow is sinking. These copepods are very tiny organisms. They are very small. They keep wandering here and there in search of marine snow. Okay. It comes in contact now. See, it has come in contact with this leaking substances. Now it comes back, and now it has identified this marine snow, and they go further down, and then they live on them. Okay, the size is exaggerated. Okay, so the marine snow size could be 100 times more than this copepod microorganisms. So that's all. I mean, this is over. Fine, sir. I'll stop now.
Sir, thank you very much, sir. Thank you.
Okay.
Very wonderful session, sir. I missed your classes, really.
Okay.
Here, we have to learn how even you are teaching very slowly and this thing, but everybody has very much interest that you have kept in the whole class. Really, your teaching ability is very much good, sir, as I'm a little bit senior to you.
Thank you, sir.
I think I learned something from you. Even my always very big voice I use it to teach, but with a small, low voice also, how beautifully can teach. I understood with you. Thank you very much, sir. Thank you so much. On behalf of the NIT Andhra Pradesh, our director, management coordinator, co-coordinator, and all the participants, we are very much thankful to you, sir, for sparing your wonderful time, valuable time.
Thank you very much, sir. I also,
Santosh? Sir.
I also thank the participants for listening to my lectures.
Please, sir, please.
Okay.
So, participants, after this session, in your group, that attendance form will be given. Thank you, sir. Namaste.
Okay, sir. See you next time. Okay.
Thanks.
Thank you, sir. Namaste, sir.
Thank you, participants. Okay.
Thank you, sir.
Okay.
All of you can say your thanks are by switching off your microphone and can give claps.
Thank you, sir.
Thank you all. Thank you. See you, sir.
Thank you, sir. Thank you, sir.